In today's video, we are going to discuss a fundamental theorem is called as Rolle's theorem. Specifically, we will be verifying Rolle's theorem for a particular type of function. Here, f of x negative a power m, x negative b power n, where m and n are positive integers. To verify Rolle's theorem for the function f of x, we need to show three conditions of Rolle's theorem. The first condition, continuity. F of x must be continuous on the closed interval AB. Coming to differentiability, f of x must be differentiable on the open interval AB. Finally, we have equal values at the endpoints. That is, f of a equals to f of b. If these conditions are satisfied, then there exists at least one point C in the open interval AB such that f dash of C is equal to 0. These conditions are sufficient conditions, not necessary conditions. Let us go through the conditions. Basically, check the continuity of f of x on closed AB. Here the function f of x is a polynomial function and the polynomials are continuous everywhere. Therefore, f of x is continuous on the closed interval AB. We can see the second condition, differentiability of f of x on open AB. Again, f of x is a polynomial function. We know that all polynomials are differentiable everywhere. Thus, f of x is differentiable on the open interval AB. This condition also met. Finally, we need to verify equal values at the endpoints. Evaluate f of a and f of b. Consider f of a negative a power n, a negative b power n. Just we have replaced x with a negative a is 0. Therefore, f of a value is 0. Similarly, f of b, b minus a power n, b minus b power n is 0. Since f of a equals to f of b is equals to 0, the third condition is satisfied. Now, since all three conditions of Rolle's theorem are satisfied, there exists at least one point C in the open interval AB such that f dash of C is 0. The derivative of f of x can be found by using the product rule. We have f dash of x, m times x negative a power m minus 1, x negative b power n plus n times x negative a power m, x negative b power n minus 1. Setting f dash of c is equal to 0, we have m times c negative a power m minus 1, c negative b power n plus n times c negative a power m, c negative b power n minus 1 is 0. Here x is directly replaced with c. Thus, we have obtained this equation. This equation implies that at least one solution C exists in the open interval AB where f dash of C is 0. To solve this equation, factor out common terms. We have the common terms c negative a power m minus 1, c negative b power n minus 1. The rest of the factor will be m times c negative a plus n times c negative b is 0. We have to set each factor equal to 0 and then solve for c. C negative a power m minus 1 is 0, which implies that c negative a is 0. Therefore, c is equals to a. Now we can see c negative b power n minus 1 also 0, which implies that c negative b is equal to 0, so c is equals to b. Third one, we have a linear equation. M times c negative a plus n times c negative b is equal to 0. Then solve for c. We have mc negative ma plus nc negative nb is 0. Let us take common c from first and third terms. M plus n times c equals to ma plus nb. Here the second and fourth terms can be brought into the right hand side. Therefore c is equals to ma plus nb by m plus n. So the solution for c are c equals to a, c equals to b, and c equals to ma plus nb by m plus n. Out of these values, ma plus nb by m plus n lies in the open interval ab. Hence we conclude that the Rolle's theorem is verified.